I hope everyone is doing good. I am Mr. Ish. Thank you for joining me. We're looking here at an extension of double integrals, which would be triple integrals with regards to volumes. But the best and the simplest way to understand how triple integrals come into play for volumes is by means of prisms. When it comes to prisms, you have to understand technically what the correct definition is. If I'm looking at something which is this, and you know what I'm drawing over here, it's a pyramid. A pyramid technically is not a prism because you don't have, with regards to the faces that you see, parallelism. But if I have here a triangular face and I translate this triangle face, like you're translating it across space, representation over here, and now you connect them, now what you really have is a prism, because here in this particular case the prism has parallelism. You have faces that are parallel simply because you have translation going on. When I'm looking here at these prisms for the purposes of this video, this is what I'm talking about, not that. We will look in this video at a couple of examples of triple integrals volume prisms. Look here at this representation. I have a function here which is y is equal to L. I have limited this function by means of a line x is equal to w. You know, horizontal line, vertical line. If I'm doing a double integral over here, this integral dx, I'm going to integrate it upwards. You can. Here's a limit, lower limit 0, upper limit w. I'm going to integrate initially with dx, but then I'm going to integrate it upwards with regards to dy from its limits 0 up to L. Now I'm going to bring in another axis. You see this axis right here which is sticking out. You have an x, y, and now I've generated a z axis. I have a specific point over here, and I'm calling that is going to be in h comma 0, and we can use capital here. Since I've used capital letters, I'm going to translate this face. I'm going to translate it back. So what I'll do is I'll have a representation which will develop, which will be like this. And you know what you've developed here is a prism. It could be square or it could be rectangular. And now I'm going to add my third integral, and that third integral is with respect to dz. Once I've done these two double integrals, I'm pushing them across through a third integral from its limit 0 up to h. I'm doing the antiderivative here. I'm getting an x with regards to w and a 0, and you know that's just a w. This w is going to squeeze over here, and then I end up having w and then 0l dy. When I do the antiderivative from here, I'm getting a y with an l and a 0. Obviously there's a w sitting outside. The difference of upper and lower, you get here a wl, you know, like a length and w. Now this length and w come right over here, and you can write a wl or lw, it doesn't matter. You have a 0 up to h dz, and all of these could have just been lowercase. I just purposely made them uppercase, but it doesn't matter. lw, and then you have a z, h, and a 0, and you get lwh. This would be the volume here of this rectangular prism, we can call it. It could be capital letters or it could be lowercase letters, but that's irrelevant. And that's the end result of this triple integral. I started here with a double integral and I pushed it across into a third integral, but the entire representation here you see is a triple integral. This right here would be the most basic of examples that I would demonstrate. Now I'll show you an example slightly more hard. Take a look at this representation. I have what here appears to be a b comma 0 and here 0 comma h. I connect them. You know I'm looking at a triangle. I can take a third axis and send it backwards, and you don't have to worry too much about my drawing. I understand drawing is a little weak over here, but I can now bring in a third point over here, and that point can very well be like an L comma 0. I'm going to translate this face. When I translate this face, I have now represented which will look like this, and we won't worry too much about the three-dimensional aspect because you can see clearly it's a triangular prism. I have this face over here which has been translated backwards to generate a triangular prism. When I'm looking at this original face, I have a line over here, this line which can be represented in terms of a slope minus h over b, in terms of equation y is equal to minus h over bx plus h. But if I'm going to do everything with regards to a dx, eventually dy, and then eventually dz, I want to convert this into an x equals format, and I can. It would be an h minus y times b over h. That's me solving for x and then doing the effect of the negative and the slope factor going on the other side. You can open this up even better and you'll have a b minus by over h. That would be the equation of this line. Here's the limit. Now what would our integral be? I'll always start here with a double integral because mentally it's easy to start small and then go big. I have a lower limit 0, I have an upper limit b, but there's a tracking going on along a curve by means of that line, b minus by over h. And yeah, this is dx, it's going to go up to h, 0h with respect to dy, but then it's going to go backwards or along the z-axis from a lower limit 0 up to an upper limit L dz. This here represents my triple integral, which will give me the volume of this triangular prism. You would integrate this. You'll have an x upper limit b minus by over h lower limit 0. Well, that's irrelevant now because this has now become the integrand of your dy integral. You would integrate all of this. You would have a by minus by squared over 2h. You know what you're going to get from here. When you do h and a 0, you're going to get the triangle area formula. You will do a bh minus bh squared over 2h. When you simplify all of this, you have a bh minus bh over 2, which is a bh over 2. This bh over 2 can sit outside now your dz integral from a 0 to an L, and this can be actually better represented as a lowercase l. When you do the z antiderivative L and a 0, bh over 2, you have your volume developed for a triangular prism, which would be half base height and L, and that would be the actual volume formula for a representation like this. So this example has been completed now, but you see how the double integral lends itself very well to a triple integral. Our third and final example looks at what is called a semi-cylindrical solid prism. It can be known by multiple names, but this right here is the official name. If you were to take a cylinder, and you know what a cylinder looks like, and you were to cut it across like this, and you take this half and you take this lower half and you separate them apart, what you're looking at is a semi-cylindrical solid. And I'll show you code over here. If I'm taking this and I'm representing a certain dimension over here, and I, for the purposes of everything being cylindrical, I'll call it an h comma 0, and I represent everything by means of a good solid. If I can draw a good solid, you see what I'm talking about. It's half of a cylinder, but the cylinder was sliced along its height. You see how it was sliced along this height? So you're getting two semi-cylindrical solids, and that right there is a semi-cylindrical solid. Anyhow, you can determine the volume of this. It's a prism. You have this face, you have that face, they're parallel to each other because the face you see was translated in a certain other dimension, developing this prismatic solid. You have to determine the integral for this, and you can radius in all dimensions. The double integral, you have a lower minus r and upper r, but in all instances you're doing a dx with respect to dy. You're thinking about an equation x is equal to r squared minus y squared because these will serve as your limits. As you can see, your finger will trace the curve, you'll converge up towards the top, and this right here would be your dx integral, which will integrate from 0 to r, 0 up to this r with respect to dy, which will then integrate from 0 up to this h and dz, and that would be your triple integral. The antiderivative here is x, upper limit minus lower limit. You'll have kind of like a doubling here. You'll have a 2 and then r square minus y square. This will become the integral input for your dy integral. Here's your new integrand. You can do substitution here, trigonometric substitution. Y is equal to r sine theta, dy is equal to r cosine theta, d theta, theta 1 and theta 2 with regards to this, and 0 and r, you'll have a 0 and then arc sine of 1, which is a pi over 2. dy integral becomes 0 to pi over 2. You'll have a r square minus r square sine square theta and then r cosine theta d theta. You've seen this so many times by means of trigonometric identity, isolation, algebra. You'll have a r cosine theta come out from this radical. Multiply with that, you'll have an r square cosine square theta. I'm just pushing the r square out. I have a 0 pi over 2. The cosine square theta will adopt this representation by means of a power reducing identity or a half angle formula. You can push the 2 out and you'll get an r square. You'll have a r square. I'm separating everything across a positive plus over here. D theta, the 2 and the 2's have cancelled out, plus r square 0 pi over 2 cosine 2 theta d theta. When you do the u substitution here and the antiderivative 0 and the pi, all of this zeroes out. You've seen it so many times. When you see it, you normally zero it out. When you look right over here, the antiderivative is a theta, pi over 2 and a 0, the difference of the two times r square, you'll have a pi r square over 2, which is right. You're looking here at a semicircle. Obviously the area should be pi r square over 2, half of a circle. This pi r square over 2 will now become the input of your dz integral. Pi r square over 2, 0 to h dz. The antiderivative here is a z, upper limit h, lower limit 0. You'll just be multiplying the h with the pi r square. You'll have a pi r square h over 2. And why does this make sense? Because the volume of a complete cylinder is a pi r squared h. When I'm doing a prismatic solid, as you see right here, a semi-cylindrical prism, it's half of a cylinder, therefore you must be doing half of a regular cylinder, and this makes sense. Pi r squared h over 2 for the semi-cylindrical prism solid. I've shown you here how triple integrals have come into play for a rectangular prism, for a triangular prism, and for something like this, a semi-cylindrical prism. Have a good day. Thank you for watching.